Hey, hello, 102 students. I thought I might take a moment here and go through the exam. I need to make a solution key so I can start grading these. And also, this would be a good time to you kind of look at your test and go through this and kind of self-grade yourself. Remember this, that the multiple choice are worth 2 points each, and the free response, which here's the free response questions, are worth 3 points each. And so I'll talk a little bit about the grading, but 3 times 10 here would be 30, and 2 times 24 would be 48. So the whole exam is worth 78 points. So let's see how we score from that. See how you do here. And the multiple choice is either right or wrong, but the partial credit is given for the free response. So that might be a little bit harder for you to self-grade, but at least you'll know whether you did it close to being right or something along those. So let's start here. Number one says, I'm happy that the first question is an easy one. Get me all started. Good for this course. Okay, it says the subject of this course is physics. So hopefully you put a D there. 2, the speed of 36 meters per second is equal to, so this is a unit conversion, and so remember there are 1,000 meters in 1 kilometer, so that kind of is that first step, so that meters would cancel off. Then we would multiply that by, I guess it would be 60 seconds in a minute. So again, seconds would cancel off. And so now we'd have kilometers per minute. So if we do that one more time, we would have 60 minutes in an hour, and the minutes would cancel off. And so now we're going to have kilometers per hour. So grabbing my calculator, here I have 36. Here I have divided by 1,000, here I have multiplied by 60, and here I have multiplied by 60. And so that's roughly 130. So number 2 should be D. Now, number 3, I didn't notice, little typo, but it says here the mass of 4.3 times 10 to the third. That means 4.3 times 1,000. That means you move the decimal 3 places, and you've got the 4,300. I'm pretty sure the author wanted C, but I'm also sure the author has a little typo. I think 43,000 was the intent of D, so I'm pretty sure C would be the correct answer, but because of the typo, I'll take C or D. They both are saying the same thing, so that's just our scientific notation. 4, again from chapter 1, more unit conversion, and something that's not as common. A furlong is 8 of them are in 1 mile. How many furlongs does a horse race in a 4-mile race? So you might say, okay, 4 miles per race, something like that. And like we did up here, we could then say, all right, 8 furlongs in a mile. And so miles cancels with miles, and then, of course, we're going to get furlongs per race, which 4 times 8 is 32. So number 4 should be D. 5, an object is accelerating. Now remember, the definition of accelerating is change in velocity, and velocity has both speed and direction. So if its speed changes, yes. If its direction changes, when its speed or the direction. So either one, including both, would change, would be the right answer. So the best answer would be C. It's certainly not only when it's speed changing. So it's not just a matter of going faster and slower, it's also part of changing direction. A child traveling at 5 meters per second on a sled passes her younger brother. If her average speed on the sled is our acceleration is 2 meters per second squared, how fast is she traveling when she passes her older brother at 4 seconds? All right, so kind of imagine going down the hill, when you pass one person, the younger brother, you're at 5, and as you go a little further down the hill, you keep accelerating, go faster and faster, and 4 seconds later, you're going to be going faster. But the idea of this one isn't so much math as it is just understanding what's meant by acceleration. Acceleration of 2 meters per second squared means you change your speed by 2 meters a second every second. So if you're already going 5, if you change by 2 more, you're at 7. The next second, 2 more makes you at 9. The next second, 2 more makes you at 11, and the next one after that, 2 more makes you 13. So 4 seconds later, you'd be traveling with a speed of 13, or put another way, you would increase by 8, because you're changing by 2 every second. There's 4 seconds, so you change by 8. And so you're already going 5, and 8 and 5 make 13. So there's the idea there. If the mass of an object in free fall is double its acceleration, and a big point here of our acceleration, so you can kind of see we're working on Chapter 2. Hopefully you noticed, 1 through 4 was from Chapter 1, and so these next 4 are from Chapter 2 here. But it would stay the same. A good lesson we hopefully got out of that, particularly that first lab, was that the accelerations is the same, whether the object has a lot of mass, a little bit of mass. It doesn't matter. All right. You throw a ball straight up at 30 meters per second. How many seconds elapse before it starts traveling down at 10? Now, we know that the acceleration is 9.8. That's roughly 10. Let's count it off in terms of 10. So if we were going 30 on the way up, we would, after 1 second, that would change by 10. Now it would be a slowing down of 10. So after 1 second, we'd be going 20. 2 seconds, we'd be going 10. After 3 seconds, we'd go 0, come to a stop. Then we would start speeding up as we fall down. So a second later, we'd be going 10. Oh, well, there it is, 10 down. So it'll be 4 seconds. So 4 seconds would be the answer. We change by 10 meters per second each second. 9, a ball with a weight of 20 newtons is thrown vertically upward. What is the acceleration of the ball just as it reaches the top of the path? Well, this is kind of back to up here. It doesn't matter how much the ball weighs. It doesn't matter if it's thrown up or down. It doesn't matter if it's blue or red. It doesn't matter if it's new or old. It doesn't matter if it's going up or down or at the top. The acceleration is always 9.8, or roughly 10. So, got to get to the next page here. But there it is. It's always 10 meters per second downward. And I know it's tempting to put 0 here, but that's its speed at its top. Its speed is 0. Its acceleration is 10. It's in the process of changing. Its value may be 0, and it's changing from positive to negative, or negative to positive, depending on how you define positive. But it's changing by something, and it's changing by 10. All right. Let's go to number 10. A parachute reaches terminal speed. All right, so I guess now we are, by the way, probably cross this border here into Chapter 3 here. But if this is my parachute hanging up like this, oh, that was a terrible picture. Let me make the parachutist in a vertical direction. So here's the parachute, and the person's falling down. So the person's being pulled down with their weight, mg, and they're being lifted up by the friction. Maybe more specifically, call it the air friction, but lifting up. The Newton's second law says the net force is what you get when you combine these two, and that's equal to the acceleration. So in this case, when they say has reached the terminal speed, that means we're not going any faster or any slower, or for that matter, turning. So there's no acceleration. That means these two are equal. That means weight equals the air resistance. So the force of the air resistance equals her weight would be the, exceed, sorry, I circled the wrong one. Equals her weight. Yeah. Equals her weight. So number 10 would be B. Okay, 11. A ball with a weight of 40 newtons is falling freely towards the surface of the moon. what force does the ball exert on the moon? So here's our two objects. We've got the ball, we've got the moon. The ball pulls on the moon, but the moon pulls back on the ball. Those should be equal and opposite. So it would be 40 and pulling it upward. And wait, a ball that weighs 40 and is freely falling towards the surface of the moon. What force does the ball exert on the moon? Yeah, upward. So 40 upward. That was threw me out there for a second. We got 40 upward and downward, but upward. Okay, so we got to get the direction right. 12. A child stands on the bathroom scale while riding on an elevator. The child's weight when the elevator is not moving is 500. Now let me just stop and review. If this is kind of the walls and the floor and there's a scale and the child is standing on the scale, let's just say it's stationary, kind of like the skydiver here. If I did a free body diagram, the child is being pulled down by the weight, mg, and so it's going to be pushed up by the scale. That's what's going to read on the scale. And if it's just stationary, I'll just call it force from the scale, force sub s, how's that? Those have to be equal because I know that Fs minus mg is the net force. That has to equal to ma. And so if you're just stationary, a is 0, and so you read your weight as long as you're not accelerating. But if you are accelerating, then the net force needs to come out to be non-zero. And so that means the force on the scale has to be something other than your weight. So again, a scale would only work correctly in a non-accelerating environment. So usually you put a scale like on the bathroom floor and there's no acceleration. But you start jumping on it, and, and maybe your feet don't even actually leave the ground. You just start, bouncing up and down on it. There's an acceleration going on and the scale won't read correctly. In fact, it'll fluctuate all over the place. Or if you are in an elevator and the whole thing's accelerating, again, it won't read right. So the only way the scale is going to equal your weight is when your acceleration is 0, which of course could occur if you're stationary or if you're moving at a constant speed. But as you're slowing down, and so remember, let me just get this clear that we're going up. A child stands on the bathroom scale while riding in an elevator. The child's weight on the elevator when it's not moving is 500. What does it read when the elevator is coming to a stop at the 10th floor on its upward trip? So it's going up. And if you're going to be slowing down, then the net force has to be down. So you're really saying here that the weight has to be more than the force from the scale. That is the reading on the scale here. So the reading on the scale, what does the scale read, is going to read less. And of course, how much less kind of depends on how much you're slowing down. But definitely has to be less because it has to be opposite to your direction. Excuse me, the net force has to be opposite. The force from the scale is still upward. It's just not much as your weight. That's why the net force is downward. That's why you are slowing down. Okay, so that's a little bit of a tough one, so I thought I'd spend some time there. In uniform circular motion, and this kind of is an extension of hopefully what you saw in 12. Maybe I'll just take a little object, but if the object is moving, say, to the right, if you push it to the right, so if the force is to the right, it goes faster. But if you push it to the left, it goes slower. And that's kind of what was going on with the elevator. The object was moving up, and so we had to have a net force downward in order to slow it down. If the net force on the elevator had been up, we would have gone faster up. We would have accelerated in an upward direction. We would have gone faster. But instead, we have a net force down, so the acceleration is down, and we slow down. And that's what these are trying to show. But this problem goes a step further. How do you make something turn? You push it sideways. You push it perpendicular. So if the pen's going this way and I push it, that's going to make it turn. If I push it sideways. If I push it in the direction it's moving, it just makes it go faster. And if it's going, this way, maybe I should go with the camera here. So if it's going this way and I push it with the way it's going, it goes faster. If it's going this way and I push it opposite to it's going, it slows it down. But if it's going up in the camera and I push it sideways, that makes it turn. So it's this sideways push that's a turn. And that's what this is trying to say. Uniform circular motion, the acceleration is parallel to the velocity. No. Perpendicular to the velocity. Yes. Sideways is probably a good way to describe it. And I'll stop there. But those other ones are no also. All right, moving on here. An airplane flying south at 40. So there's 40 to the south. What is the magnitude of the plane's change in velocity if later it is flying west? Okay. So we have to take the initial and put a change to it and get west. Oh, and I didn't draw my grid very good. Normally, you draw north up and south down, and I did that. But you draw east to the right and west to the left. And we want to end up going west. Okay, so I would say, okay, so at first you're going to the south at 40. Then there is going to be a change, and so it would look like this. Initial plus change would equal final. Maybe it reads better if you write it as change is final minus initial. Okay, but I'm going to draw my pictures here, and that's kind of what this whole chapter was all about, the little vectors and the arrowheads. But I got to have my initial. I got to add the change to get the final. Now, I want the final to be 30 to the west. So that would have to be the change. So it would be initial plus the change results in 30. Okay, so what would it be? Well, this is a Pythagoreans theorem. It's also the magical 3, 4, 5 right triangle. So this must be 50. And it's not really a 3, a 4, and a 5. It's 10 times that. So it's a 30, 40, 50. All right, so it's got to be 50. It's even got to be kind of off at this angle. So that angle's kind of pointing off in a kind of a northwest direction. Now, not quite 45 degrees. So to say exactly northwest wouldn't be correct. But they're not even asking for direction here. That's for our next level of class, where we'll say the direction and the angle, and we'll go through some trigonometry to get that angle. But for this one, it's just to kind of begin to learn to use these arrowheads and these vectors. And so to realize that, you know, when they ask for the change is what you get when you take initial plus the change, you get final. Or put another way, change is final minus initial. All right, so anyways, it's 50 there. That could be a little tough one. Okay, by what factor does the centripetal acceleration change if a car goes around a curve twice as fast? Now, the magical equation is this v squared over r, and if you remember from the video lecture, I promised I would work this out when you guys knew calculus, so when you get into Physics 121, we'll work this one out. But nonetheless, we could still use the formula without proving it, and so v squared is the key. And so if you take a factor of 2 but you square it, because it would be speed squared, you get a 4. And that was really the point of this problem, was to make sure you just didn't say, oh, it's doubled. Kind of a easy thing. Oh, well, if this doubles, that doubles. No, that's not true when you have squares in them. That would be true for things that are what we call linear, but in mathematics, when they're quadratic or cubic, you square something that is squared, or you double something that is squared, that's 4 times. Now, if you double something that is cubed, that's 8 times. So, just got to watch our math. Which of the following statements about a projectile is true? The horizontal and the vertical components are independent. Yes. The force on the projectile is constant through the flight. Yes. The acceleration of the projectile is constant throughout the flight. Yes. In fact, I guess those would be kind of saying the same thing, B and C. So they'd be all of A, B, and C. So 16 must be a D there. Two spacecrafts in outer space are attracted to each other with a force of 20 newtons. All right, so if I was doing universal law of gravity, I guess I would have this. Okay. What would be the attractive force if they were half the distance apart? Okay, now this one is a little bit like the centripetal acceleration where I have a square, because they're asking me to take a 1/2 and square it, so that's a 1/4. And it's in the denominator, so when you have something like 1 over 1/4, you flip it and you get 1 over 1 times 4 over 1, which is 4. So a quarter smaller in the bottom makes the quotient 4 times bigger. So if it was 20, 20 times 4 would now be 80. So 80 times bigger. Okay. The gravitational constant G in the law of universal gravitation is believed to be a constant with time. Yes, absolutely. We haven't been around long in history to measure it throughout time, but since we have been measuring it for almost 200 years, it has not seemed to change, and hence we call it a constant. So definitely is true. But also some of the evidence we have with the motion of the planets that go way back in time would only work out if that stayed a constant. So we've got a lot of evidence to say G doesn't change with time, but there's always some speculation about that. Really, does it? I mean, come on, we've only been measuring it for 200 years, and we know the universe is 13.8 billion years, so if it's changing slowly enough, we might not have seen it over the last 200 years. But again, looking at the formation of galaxies, we could look back and pretty much say it just wouldn't work out if it wasn't constant for at least the last billion years. So it's probably a constant for the whole 13.8 billion years. At least that's our current understanding. Okay. It's believed to seem the value throughout space. Yeah, again, that's kind of our look. We look at the formation at our solar system and our galaxies and other galaxies, and they seem to point to the same kind of motion. So we think it's the same all throughout space, even though we really can't measure much of space. I mean, we can go from one side of the Earth to the other. In fact, none of our probes would have made it as far as they did out to Jupiter and Pluto had it not been the same. So our probes worked, so we're convinced throughout about the size of our solar system. We've actually got a chance to test it. So, but again, the size of our solar system is really small compared to the whole universe. But again, to the best of our speculation here, it's the same throughout. It doesn't look at all. There's no evidence, I guess, to say that it changes, and a lot of evidence to say it is the same. It's also what we use to determine the mass of the Earth and all the other planets, and so I guess all of these are true. So 18 should be D. Now, in a typical 24-hour day, if you remember this discussion about tides, if you take a planet, I'll call it planet Earth, and put a liquid on it, especially since that's the only planet we know to have a liquid on it. Okay. Liquid water. Yeah. I can go down a long road to that, but I better not. But when you put something near it, like on the moon or the sun, it elongates it in both a forward and a back direction. So if you're on the Earth spinning around in a 24-hour period, as it gets elongated in both front and back, you're going to go into a bulge, out of a bulge, into a bulge, out of a bulge as you go around in one day. So you're going to go into two bulges and then in the shallow parts. So you'll have two high tides and two low tides. So there we go. Two high tides, two low tides in a given day. And so that'd be D. Mercury, this might sound a little familiar like the Mars problem we did on the homework. Mercury has a radius that is about 38% of the Earth's radius. It has a mass of only about 5.5% of the Earth's mass. Estimate the acceleration due to gravity on Mercury. Well, hopefully one of the things you got was that if you take two pieces, the universal law of gravity and Newton's second law, and you put them together, you get the equation for what the acceleration would be on a particular planet. And in this case, since it was open book, you could actually look up the mass of Mercury, or you could look up the mass of the Earth and multiply by 38%. You could also look up the radius of Mercury, or you can look up the radius of Earth and take 5.5% of it. But like I did on the homework video, and I'll show you here, it's probably better if you do this one this way. Take the mass, I think I said that backwards, 5.5% of the mass and radius. No? No, I can't remember which way I said it. Anyways, but it's 38% of the Earth's radius. So downstairs where the distance is, I will go 0.38, and I'll put r sub e, and I'll square it. And up at the top, for the mass of the planet, it says the mass is only about 0.055 the mass of the Earth. And the reason that is useful, let me get some room down here, is because if you put the numbers out in front, and so I'll take the 38, but don't forget that the 0.38 is squared, and then you put the g and the mass of the Earth, and then the radius of the Earth, and you square it, all of that would be that magical 10 or 9.8. So we don't really need to look anything up here. We can just take our 9.8, multiply by 0.055, and divide it by 0.38 squared, and coming up to about a 3.7. I have a feeling they might have done 10 here. Let me try a 10. 10 times the 0.055 divided by the 0.38 squared, would be 381. So that's the closest one there to match up. All right, 21. How fast would an 80-kilogram person need to run to have the same momentum as an 18-wheeler, which is 24,000 kilograms, rolling at a 1 mile per hour? So, mass 1 times velocity 1 is the momentum, and you're saying, okay, how does that compare to an 18-wheeler? So if you take the mass of 80 kilograms and the speed of that person, which we don't know, and you say, I want it to be equal to the mass of an 18-wheeler, so 24,000, going at a speed of 1. Now, the units here would be miles per hour. You might even be tempted to go to meters per second, but don't, because once you get the answer, you just have to go back to miles per hour. So I'm going to leave this as miles per hour so that this will come out in miles per hour. This is in kilograms, which are going to cancel off. And so it might look kind of funny because you have mixed units from the metric system and then the English system, but so what? Just follow the rules of our units, and in this case, the units that are in metric cancel off, so the English system gets left over at the end. Okay, so this would be 3,000, and divided by the 80, I guess that's 300. Don't really need a calculator for that one, but so 21 would be A. Why is skiing into a wall of deep powder less hazardous to your health than skiing into a wall of brick? So crashing into, the powder versus crashing into a solid object. Assume that both cases you have the same initial speed and you come to a complete stop. So if you recall this part of momentum, so I guess this is chapter 6 type of one, it's the change in momentum over the time taken. And so the force depends on a lot of factors, and a big one is the amount of time. But of course, the other one's a change in momentum. But if you read this carefully, they say in both cases you have the same initial and final speed and the same mass. So the numerator is going to be the same if we were calculating this for the crashing into the powder or crashing into the bricks. And so what makes the difference would be the contact time. Okay, and the numerator is called the change in momentum, and so, or the impulse. So the impulse is less, makes no sense. The change in momentum is less, is the same statement. So all of this is about the contact time. And there it is, the increased stopping time in the powder would mean a smaller stopping force. Okay. A coach hitting pop flies to outfielders, if the ball has this mass, stays in contact with the bat for 0.04 seconds, and leaves the bat with a speed of 50 meters per second. What is the average force? So again, same formula, but now I'm going to plug things in. And in this case, the final momentum is the mass, which is 0.145 kilograms. And notice, maybe now the little tricky part of this problem, is I'm going to need my mass in kilograms because look at the answers all in newtons. And remember, a newton is a kilogram meter per second squared. So even though they gave it to me in grams, I'm going to plug it in kilograms. Now the final speed is 50 minus the beginning, which they don't really say it's at a stop, huh? The coach is hitting pop flies to outfielders in contact with the bat. If not zero, it's small. I don't know if you've ever seen anybody kind of do this trick. They just kind of toss the ball up and hit it. And they toss and hit and toss and hit. So the initial momentum is very, very small. And I'm going to just take it as a zero because we don't really have anything else to work with here. Especially since it's going off the bat at a huge speed. This is over 100 miles an hour. So these are serious pop flies. It must be big kids or something. Okay. And then if you look at the units here, this is meters per second and this is second. So that's going to be kilogram meters per second each second, which is in a newton. Good. So grabbing my calculator, be 0.145 times 50 divided by 0.04. And we're looking at about 181. And so A would be the right answer there. Now, finally, the last one, at least on the multiple choice, and we can get to the free response. It says, Carmen is standing on a giant skateboard initially at rest. And so here is this person on a giant skateboard initially at rest. That was a nice way of saying the total momentum of the two of these is zero. If we ignore the frictional effects on the floor, what is the momentum of the skateboard if Carmen walks to the right? So we're going to walk and have a momentum. We don't really know how fast Carmen is going to the right, although it could be something like this. Let's say Carmen's a big person, so it could be 100 kilograms at a speed of 5 meters per second. Okay, that's just one of many options. But what we definitely know for sure is they have this much momentum, which means then the skateboard has to match that momentum to the left because the total can't change. So this is a conservation of momentum problem. Okay, and so that's it. What is the momentum of the skateboard? And so the skateboard, the best answer would be 500 to the right. Not left and not just 500 and certainly not zero, but to the, to the left. Sorry, circled the wrong one there. To the left. Carmen's to the right. The skateboard then would be to the left. All right, good. Well, I hope that was somewhat helpful and a learning experience if you missed anything. Let's move on then to the free response questions here. And I'll grab my little notepad here and put a little number 25 here and say, all right, let's look at this first one. It says a rock is released from rest. Okay. Neglecting air friction, how far does the rock fall in 3.5 seconds? So hopefully this sounds a lot like the stuff we did in chapter 2. And one of the formulas, not the only one, but one of the ones you could use would be this one. This is the one we said was only valid when you had a starting speed of 0. Now, the other one we said would always work. So in some sense, I prefer this one because it doesn't have this restriction. But this one's an easy plug right into. I can just put a 1/2. I could put my 10 meters per second squared for the acceleration, and I could put my 3.5 seconds and square it. And so the squared and seconds, leaving me with just meters. Oh, I should have left myself some room. Meters. And so if I grab the calculator, I got 1/2 times 10 times 3.5 squared. And so this is going to be a 61.25 meters. Now, I suppose if you want, we can do the 9.8. I'll take either one. I'll be looking at them and able to issue you partial credit if you did it partly right, and I can tell if you did a 10 or a 9.8. So either one of these two is correct. Now, you could have done it this way. This one, I think, is probably a little bit longer, but you might have done something like this. You know the speed changes by 10 every second. So after 1 second, it's going 10. After 2 seconds, it's going 30. After 3 seconds, it's going 30. After 3.5, it's going 35, halfway up. So if you take a starting speed and an ending speed, add them together, divide by 2, you'd get the average. So it starts at 0, gets up to 35, add them together, divide by 2, that's the average for 35 seconds. And of course, seconds is going to cancel, and you're going to be left with meters. So if I do that, I would take the 35 and cut it in half and then multiply by the 3.5. And not a surprise, I get the 61.25. You could even do the same thing with the 9.8, but then it might be a little harder. Instead of counting it out, I should use a calculator. But let me not go down that road too far. This I'm thinking would be coming to your mind first. But 25 and 26 really go together because 26 talks about this dog. So a dog is running at a speed of 10 meters per second and slows down uniformly to a speed of 3. What's crucial about this problem is right away you hopefully recognize you can't use this formula. There was not a starting speed of 0. So I can't do that. It does say how far does it travel, so I need to do this problem. And since they give me initial and final speed, it actually makes it pretty easy. They start at 10, dog slows down to 3, so if I add them together, divide by 2, that's the average speed of the dog. And apparently the dog took 4 seconds to do this. And so this would be in meters per second, and seconds would cancel, and you'd be left with meters. So let's see, 10 and 3 is 13. Divide that by 2, and then multiply that by 4, and we're looking at 26 meters here. So that's how far they would go. But again, hopefully you recognize they kind of fit together right out of chapter 2, one and the same, because I'm going to say the same thing about 27 and 28. 27, hopefully you recognize it's right out of chapter 3. It's about Newton's second law. It is kind of a hard one, though, because there's a temptation for students to do only half the problem. Watch this. It says, when a force of 55 newtons is applied to a 2.5 kilogram chair on a flat floor, it slides across the floor with a constant speed. Now I'm going to come back to that, but leave the second part of this. It says how much force must be applied to a chair to have an acceleration of 2.5. So the first step might be to say, well, look, they gave me mass and they gave me acceleration, and that's true. They gave me a mass of 2.5 kilograms for the chair, and they say the acceleration is 2.5 meters per second squared. And so that looks like a 25 squared, so that would be 6.25, and kilogram meters per second squared would be the units, which comes out to be a Newton. And it's very tempting to stop right there, but don't, because that's only halfway through the problem. That right there is the net force, and that's not what this question asked. It says, how much force must you apply? And so maybe if I draw a little free body diagram here, and so maybe the chair looks like this, and I say, okay, I'm going to be pushing it this way. The rubbing of the chair legs on the floor is going to create some friction. Now, do I know that friction? Yeah, I really do. It was hinted at right here. It said, see, when you applied a force of 55, it went across the floor at a constant speed. So that means you had a net force of 0. So when you were applying 55, it didn't accelerate, which meant your frictional force was 55. Now to get it to accelerate, you got to push a little bit more. But it's not at 6. It's actually 6 more than the 55. It would look something like this mathematically. You've got the net force, and the net force is the force you apply minus the friction. So I'll say it again. Don't stop here at the net force. That's what you calculated. This number right here, 6.25. But the question is asking for this force. And so it's really easy to, like I say, stop because, hey, you found a force. But that's not the force they want. If this question had been find the net force, yeah, then you would have stopped. Or if this was find the friction, then you probably would even have read the second sentence. You would just say, oh, it's 55. But what this question was asking is the force you're pushing on it. So depending on which one they're asking for is going to dictate how far I have to work through this problem. And so I got to find that one. So I'm going to move this over to here, and then that makes 61.25 newtons. So that would be the final answer. So this is halfway. This is 1.5 points because you did half the problem right. So then you get another 1.5 by doing the rest of the problem, which is part of realizing the net force is 55, and part of it realizing that the net force is not what they're asking for, and part of it's realizing how do you get the net force? It's the difference between them. All right, well, I hope that one went well, because like I said, that is a little bit of a harder one. And I would put number 28 in that same category, and maybe even a little harder still, because number 28 says that we're dropping something. It looks like a relief package. So what did it say here? A 4.2 kilogram relief package has an acceleration of 2.5 meters per second each second and is dropped from a helicopter to our stranded victims in the canyon below. Okay, so what is the force of friction? Now, in this case, I guess it would be air friction. But let me just start with the same step I did in the last problem. Let me just say the net force is mass times acceleration. So, again, I would be tempted to stop after this, but I'm not going to. It's 4.2 kilograms is the mass, and the acceleration is 2.5 meters per second squared. In fact, if there was no friction, we know its acceleration would be 9.8. So the whole reason it doesn't go at 9.8 is because there's air friction, which is ultimately the question here. It says, what is this friction? Okay, but let me just start with the first half. So 4.2 times 2.5 gives me 10.5. So the net force is 10.5. But let me draw the free body diagram again for the second half, because what's pulling it down is gravity mg, and then of course what's stopping it is the friction, the air friction, the rubbing of something. The other problem, it was the the chair's legs on the floor. Now the rubbing is between the relief package and all these air molecules. But I'd set it up exactly the same. I'd say, okay, the net force then is the weight of it minus the friction. And again, had they asked for the net force, I would be done once I wrote 10.5. But they didn't. They asked for that one. So I got to put in the net force. And then also I need to remember the weight is mg. And so in this case, it's 4.2 times roughly 10, which of course makes 42. So when I move friction to the other side, I'm going to get a 42 and then minus 10.5. Let's see, if I subtracted 10, it'd be 32, so another half would make 31.5. Okay, so my frictional force must be 31. So in this picture, I'd say, okay, gravity is pulling it down at 42 newtons. The air resistance is pushing it up or opposing the motion at 31.5 newtons. Of course, putting those two together is the net force. So again, don't just give me the net force. Hopefully you did the second half here. But like I said, easy to stop there. All right, moving on to the next chapter, which I guess this would be chapter 4, projectile motion stuff. Here in 29, it says we have a football that is punted, and so maybe the football looks something like this. And it's, of course, heading out, maybe something like that. But they describe it, they said the football is kicked with a horizontal speed. So it's got 15 meters per second in the horizontal direction. And at the same time, it has an upward speed of 22 meters per second. And not really needed for this problem, but if we did Pythagoreans Theorem here, 15 squared plus 22 squared, and then taking the square root of all of that, we would get the total speed of 26.6 meters per second. But I'll say it again, unnecessary. That was just kind of my own curiosity and also pointing out that, that could have been the problem. But this one is about the accelerations here. And so it really says in 29 then, what is the horizontal and vertical speeds 2 seconds later? Well, hopefully what you got out of this chapter is that the acceleration in the horizontal direction is 0, and the acceleration in the vertical direction is that 10 meters per second downward. And my little comment about how do you do two-dimensional motion, you just do one-dimensional motion twice. So we make a little chart, and we just talk about horizontal motion in one chart and vertical motion in the other chart. All right, so if they're asking for the speed in the horizontal direction, so I'll say speed horizontal, it's still going to be 15. It never is going to change in the horizontal direction. Doesn't matter if it's 1 second, 2 seconds, 3 seconds, 4 seconds later, the horizontal one doesn't change. There's no acceleration in the horizontal direction, or at least until it hits the ground again. Then there is an acceleration and a force in the horizontal direction. But as long as it's in the air, as long as it's a projectile, gravity pulls only down and nothing horizontal. All right, so that's half the problem. What is the speed in the horizontal direction? The other one then is what is the velocity in the vertical direction? And so we know the acceleration is supposed to be 10. Now, if it's going up and the acceleration is down, that means it would slow it down. So 1 second later, we would take 10 away from this, so we would be at 12. And a second later, we would take another 10 away from it, so we're at 2. And we're still going up. I don't know if the up is required here. It doesn't really say what direction. So what is, and it just says speed, but all right. but just for your clarity, it's still going up, but it's getting ready to stop and then start coming back down. But 2 seconds later, it's moving upward still, but barely. And it's still moving across the field horizontally here. And so this is going to keep going across the field there. Okay. And so that was the idea, and I'll say it again, projectile motion. It's to do the one-dimensional motion twice. And you see that on the next problem, number 30. Because number 30 says, okay, now using the information from back on problem 29, how far did it go? And so again, let me encourage you, make 2 columns, one for the horizontal and one for the vertical. Because again, how do we do 2-dimensional motion? You do 1-dimensional motion twice. All right, so if we go back to our 1-dimensional motion, we can just say that the distance it moves horizontally is the average speed horizontally multiplied by time. And the average is pretty easy to figure out. It started at 15, it finished at 15. I mean, if you really want to calculate it, go, okay, it starts at 15, finishes at 15, add them together, divide by 2, and you get 15. I mean, the horizontal one doesn't change, so its average is just 15. I don't think it's even necessary to have to do a calculation. It's just always 15. So its average is always 15. Now for 2 seconds here. And so this would be 15 times 2 or 30 meters. So it will go, 30 meters in a horizontal direction by this point. But it's the same thinking for the distance vertical. And then this hopefully illustrates that I'm just doing the same calculation. So I'll say it again. Projectile motion is to do 1-dimensional motion twice. Once for the horizontal, once for the vertical. So I'm going to do the same logic for the vertical. Now the vertical is a little bit harder. We got to come back here and realize that the final speed is 2. And the initial is 22. So I would go 22 plus 2 divided by 2. That's the average of those 2 numbers. The starting speed, the ending speed, add them together, divide by 2. That's the average. And then for 2 seconds. And so what's that? 24. You can kind of see the 2's would cancel off here. Or you can go 24 divided by 2 is 12. 12 times 2 is 24. So it's going to be 24 meters high at this point. So it's 24 meters high, and it's 30 meters over, and it's almost reached the top of its path before it's going to start coming back down. So hopefully, again, that was helpful. All right, so let's look at 31. 31 says we have a 180 kilogram motorcycle. It's turning, going at a speed of 16 meters per second. The turn is part of a circle of radius 12. What is the centripetal force? Well, again, this is right out of... Yeah, what chapter is this? I guess this is also chapter 4. Yeah, so we haven't really got to chapter 5, but it's the other part of chapter 4. Chapter 4 had the projectile, which we did too, and then it had the circular stuff. But this is that mv squared over r. Again, that's that equation that when we were doing the multiple choice, I said that, hey, let's derive this when you learn calculus, but for the meantime, let's just learn it now, and then we can use it. So in this case, the motorcycle, to make this turn, would need this much force on it. So it's 180 kilograms. Going at a speed of 16 meters per second squared and making a turn that has a radius of 12 meters. Now, if you look carefully at your units, this would be a kilogram. And at first it would look like meters squared, but we can cancel one of those. So it's kilogram and only 1 meters over second squared, and that is a Newton. So yeah, this is going to come out to be newtons. And we're going to need a calculator for it. So 180 times 16 squared divided by 12. And so looking at 3,840 newtons is the amount of force needed on this motorcycle. And so presumably it gets that force from the traction between the tires and the road, so it can actually make the turn. If it can't get that much force from the traction, well, it can't make the turn, and motorcycle is not going to follow the road. It can't turn that much if it can't get that much force. So, like I said, hopefully there is enough traction there. Otherwise, the vehicle is not going to make the turn. Okay, so now this is 32. It looks like the only one from chapter 5. And there's a gravitational force. Okay, and so G m1 m2 over r squared. So this is how you calculate the force between any two objects. So here, the gravitational force between the planets Jupiter and Saturn at their closest point. And then it gives the mass of Saturn and the mass of Jupiter and the distance between them. Now, the one thing that needs to be a little careful here is to recognize the units for G. They're in newtons, meters squared over kilograms squared. So that means your mass needs to be in kilograms and your distance needs to be in meters. Now, as far as mass goes, that's fine because they list the mass in kilograms. But distance, they do not. They list it in kilometers. So one thing that you want to be careful with here is you make sure you put your distance in meters. So let me put the first mass. Let's see. I'll put Saturn first. 5.68 times 10 to the 26th kilograms. And the mass of Jupiter, 1.90 times 10 to the 27 kilograms. And their separation, 6.52. And it says times 10 to the 8th kilometers. So in place of kilometers, I'm going to put 1,000 meters. So this right here is really 10 to the 11th. Remember, you add exponents. And then you can see meters squared would cancel with meters squared, and kilograms squared would cancel with kilograms squared, leaving the appropriate unit of a force, a newton. All right, so we got some big numbers here to work with, so we need our calculators. 6.67 times 10 to the negative 11 times 5.68 times 10 to the 26th times 1.9, I'll put 0, why not, times 10 to the 27 divided by 6.52 times 10, and there it is, to the 11th, squared. Enter. All right, and I get a force of 1.69 times 10 to the 20th newtons. So there's the one and only free response on universal law of gravity. The other ones were having two. It looks like Okay, so now we are almost done, 33. 33 and 34 go together. They're momentum ones. Okay, so here we have a 1.2 kilogram sandbag is thrown with a speed of 7 at a bigger 2.5 kilogram sandbag. The bigger sandbag is traveling towards the smaller sandbag at a speed of 2. If the two bags hit and stick together, what is the speed and the direction of the combined? So hopefully what you got out of chapter 6 is that there is a before and after. And that is the momentum before equals the momentum after if you consider both objects. So let's go before. Before the collision, we have a mass of 1.2 kilograms traveling with a speed of 7 meters per second. And I can add to that the bigger sandbag. Uh-oh. I'm going to cross over my line. Let me readjust my line here in a second. But it's 2.5 kilograms traveling. And there's an important word here, towards the smaller one. So it has a speed of negative 2 meters per second equals. So there's the line. Now, if they stick together, we can now think of them as one object. So the 1.2 and the 2.5 would make a 3.7 kilogram object traveling at some speed. And that's going to be the key right there. The speed is what? And of course, our positive direction is in the direction the original one is going, the smaller one, and the negative is the direction of the bigger one. So it'll be interesting to see if this comes out to be a positive number or a negative number. So it's 1.2 times 7. And the other momentum is 2.5 times a negative 2. And so that's the momentum, 3.4. By the way, notice it's positive. So when you divide by 3.7 on this side and get a number, it is a positive number. And the positive means it goes in the direction of the smaller sandbag. Okay, two stick together. What is the speed? There it is. There's the number, 0.919, and the direction. There's the direction. And 34 is the same thing. Let me put my chart more in the middle this time. I kind of didn't give me enough space here in the before and after. But here we have, again, two objects. So we have momentum conserved as they interact. We've got to consider both objects. So the first object is a 0.65 kilogram rubber ball, and it's thrown at a stationary cart. Maybe I'll keep reading here. The rubber ball hits the cart with a speed of 12 meters per second and bounces off the cart, traveling backwards to the thrower at 4 meters per second. Okay, so before the collision, I have a mass of 0.65 kilograms traveling with a speed of 12. So I'm going to pick a positive 12. That's the direction that the rubber ball is originally thrown. Okay, because the rubber ball cart at a speed of 12. Okay. Now, the other object is the 3 kilogram cart. So 3 kilograms, but it's a speed of 0. So there's the momentum of the two. I guess you could really ignore that one and say that one's 0. So this is 0.65 times 12, if you kind of want to do an intermediate calculation. So 7.8 kilogram meters per second is the momentum before the collision. But it's also going to be the momentum after the collision. But here, they don't stick together, so we can't think of them as one object. So that's what makes, I think, 34 harder than 33. 33, we just thought of as one object on the other side. But now we have to leave them alone as separate objects. So it says that the rubber ball, so the rubber ball is still 0.65 kilograms, but it bounces off the car traveling backwards at 4, so its speed is negative 4. And that might be another hard thing, is that negative, although that's the same thing we did up here in 33. So hopefully you recognize that you need a negative in 33 and that you also need a negative here in 34. Now, the other object is 3 kilograms, and I'll just put a final speed of it. We don't know what its speed is. Now, if I do this 0.65 times a negative 4, this is a negative 2.6 kilogram meters per second plus 3. So if you'll let me do 2 steps here, this is the 7.8, and when I move this to the other side, it becomes plus 2.6. So then when I divide by 3, I get about a 3.47 meters per second. I should have put my units kilogram because kilograms will cancel out all the way through, leaving with units of meters per second. So there would be the final speed, and it's positive, so that means it's going in the same direction that the original rubber object was thrown. But I don't think that was ever in question, what direction it goes. The cart, if the cart's here and we throw the rubber ball comes and hits it, boing, bounces off. The cart goes in the positive direction. So they don't even ask for the direction of the rubber cart. They just ask for the speed. I guess direction is just so obvious. But it did come out to be a positive number, so it would be in that same direction as the originally thrown object that we labeled as positive, just like in 34, coming out to be positive. It would be in that direction. All right, well, I hope your self-grading went well, and if you made any mistakes, hopefully you've learned from those mistakes. And I will get to grading your stuff soon. I know that I have a big day Friday, tomorrow with Zoom help sessions, so I'll probably get started a little bit, but really Saturday and Sunday will be the grading time. All right, take care.